Well, welcome to another RDWorks Learning Lab. Today we're going to take that big step with this machine and change the tube. Now, I mentioned before that we needed to change the tube, but today I hopefully am going to be able to demonstrate what happens when we do change the tube, what we get after we've changed the tube. I'm changing a tube on here which to all intents and purposes is perfectly okay for most people. But for me, where I do quite a lot of detailed photo engraving work, it's lost its edge. It's become a blunt pencil. It doesn't produce the crisp dots that it did originally when I used this machine to develop the compound lens. We're going to do some preparatory tests before we change the tube and after we change the tube to compare the difference. Have I wasted my time and effort and money? We'll wait and see. The first reference test that I'm going to do is in this block of acrylic. We're going to set the power to maximum, which is 85% for this machine, which is about 22 milliamps for a 60 watt tube. So we're going to see what shape is evaporated away in this block of acrylic when we run the beam into it for 10 seconds. Now here I've got a small tube that I've connected up to my air assist just to give me a little puff of air, because if I don't do that it'll catch fire when I fire full power at this block. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You'd probably say that's quite a nice burn. It's got a point on it, but it's not the best point in the world. But what I'm using for photo engraving on this machine is about 15% power. So let's do the same test at 15% power and see what happens. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Big difference, I think you can see. Now we're going to do the same two tests. We're going to do it on the opposite side of the block and line up approximately where they are so that we can look at the top of the block and do a comparison. So using the calibration charts for these machines, I've set this one up to about 70%, which gives me roughly the same sort of output power as I was expecting from the previous machine. So we've got a reasonable comparison here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is what we'd engrave at on this machine. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, I think you can probably see that there is quite a significant difference in the shape or the energy density profile across those beams. I mean, this one here, for example, you can see at my engraving value, it's really lost its point, whereas this one has still got a nice sharp point at 15% power right down at the bottom. It hasn't lost its shape even though I've reduced the power, whereas this one loses its shape as soon as we reduce the power. So this is the one that we're going to change, and we're going to see if we can get it even better than this one. Now what you must remember is this tube here is only 2.5 years old, whereas this tube here is 4 years old, and it looked much the same as this when I tested it 4 years ago. Now I thought this would be a nice comparison between the two machines, but in fact it's not as good as I thought it was going to be, but it's still significantly different. You can see that this one has got a lot more blackness in its colour. When you start looking at it in detail, I mean this one is actually quite a nice picture, and most people would probably be very, very happy with that, but I know what the quality is that I'm looking for, and that is not it. Let's do a little bit of a comparison and I'll show you the sort of detail that I'm looking for. You'll see down here, look, we can see every single hair sticking out down here, whereas here they've just washed out. There isn't enough power, enough sharpness in the pencil, if you like, to draw the detail in those hairs. You can see all these hairs are lovely and crisp with a dark background against them. Well, here you've got really almost like a grey background, and it doesn't help the definition of these hairs. You'll see exactly the same thing on the other side of the picture. Look, you've got all the hairs down here very clearly defined, and yet down here it's almost like fog. It's not, there's no detail down here at all. That's the reason why I'm changing the tube. I cannot achieve the same results on this machine that I can on my old China Blue machine. Okay, now for this little demonstration I'm going to lock you inside the machine, close the cover, and all I say is hold your breath because there might be a little bit of smoke. Baltic birch plywood, which I've just cut at 35mm a second. The pieces have not fallen out because I've actually put bridges on them to make sure they don't fall out. And the reason I don't want them to fall out is because, ta-da! Look at all the crap that's come out the bottom of the cut. Yeah, so these pieces are bridged in. I think the bridges probably could be a little bit thinner. I've got 0.5mm bridges in here, but I may well take them down to about 0.3 or 0.2. Then they'll literally just pop out. Normally, all this horrible sticky crud would have gone down into my filter unit and clogged the primary filter up. I've got a Purex recirculating system here, which it's not cheap to maintain, and so I like to protect it as much as possible. So I've got, this is my primary condensing filter, then I've got a secondary primary filter inside the machine there, which is a very cheap foam which I can replace very cheaply. So I've got two levels of primary filtration before it even gets to the primary filter in the Purex unit. Now the reason why I'm doing that is because even the primary filter in that unit, which lasts somewhere in the region of maybe 6 to 8 months for me, and I don't do that much work in it, costs about £60 a pop. You certainly don't want to be replacing that very often. The HEPA filter with the active carbon in it is another 250 quid, which I've just had to buy. So I've just spent out £400 for a complete new filtration set to go in this machine. And as I've shown you several times before, a little bit of acetone, and I can clean my filter for free. Okay, so it cuts Baltic birch plywood at 35mm a second. Does that mean to say I'm absolutely insane to change this tube? Because it's a perfectly good cutting tube. There's some characteristic of this tube that has changed at low power. Now I've got no idea what that characteristic could be. It may well be that it is the cathode beginning to oxidize up a little bit, and that makes it more difficult to energize the tube at low currents. I really don't know. I don't understand enough about the physics to be able to say what the problem is. All I do know, as I've demonstrated to you, is there is a problem, and I don't have that same problem on my other machine, and it was not here 6 to 9 months ago when I developed my compound lens. So I'm going to do the insane thing of changing what would normally be a good tube to most people, but I just need to understand if I can get the crisp engraving performance back by putting in a tube that will have a nice sharp characteristic at low power. Now, just out of interest, one of those pieces didn't come out very cleanly, and I've mentioned this a couple of times before, but I will show you because it's a classic example of why you can have a perfectly good cut for 99% of the time. If we look carefully in here, you'll see that we've got a void. And what's happened is that void has filled with smoke. The smoke has absorbed the energy and it's prevented the cut from going through properly. Now, just to undermine my confidence even more and convince me that I'm going mad, I've done a calibration chart for the machine now, today, which is the yellow highlighted line, and here's what it was 2.5 years ago in July 2017. And if you'd have shown me this chart as your machine, I would have said, oh, this is a pretty good machine. Look, actually, even though it's changed, it's actually got a very good linear relationship, which is actually a better relationship than this curved relationship that it was 2 years ago. The current is still nice and steady, so there's nothing wrong with the power supply. The only change that's taken place is with the tube itself, and if anything, the tube has got a little bit more powerful at the top here. Nothing special, so this looks like a very good tube until we look at that and we see that the diagram is not telling us every part of the story. I had an incident a few weeks ago. A guy phoned me up and said he got a brand new recce, you say tomatoes, I say tomatoes, tube. It was sold as a 130 watt tube and he tested it at 127 watts. So what was the problem? Well, the problem was the mode looked like that. He couldn't even cut 3mm acrylic in one single pass. Even at full power, it was looking just like this. Measuring the power is not the full answer to the performance of your tube. The shape of the beam is the most important part of it. The energy distribution or the light intensity within the beam is the most important element. I've undone all the metal clips and box. Oh, with a box inside another box. We have arrived. And wow, that is nice. Now the most obvious thing that we shall see is the fact that the tube down the centre has got a very slight pink hue to it. And that means it's coated with a very, very thin layer of gold on the inside to try and make this into a long life tube. And just as proof that it comes from SPT, it's got that on the label here. So although it's branded as a cloud ray, as I've told you many times before, these tubes actually are A-grade tubes from SPT, and Cloud Ray have got their own branding arrangement with SPT. So these are excellent quality tubes. And while we're here, down in this part of the world, anybody recognise that? This is my flame damaged Chinese machine that somebody gave me. Okay, I threw away the top half of the machine, but this bottom half was too good to throw away. So it's the basis of my current laser workbench. I needed to make sure that it was a reasonable fit for my existing machine clamps. Yeah, I could use the clamp system that I designed, but if I do that, it means I shan't be using the same setup procedure that you guys might want to use. So I'm going to use the existing clamp system that's on the machine. I believe it's the same diameter. Let me just check. Yep, that's what we've got at the moment, 55. And this is 55 as well, give or take a few parts of a millimetre. Well, the other thing that I've got to check is this piece of kit here, which is the HV power supply. Now, it clearly says on the top here, from Think Laser, that this is a power supply, 60 watt PSU, for use in machines with tubes up to 60 watts. I've got a 70 watt tube. Does that mean to say this is useless? I think the answer is no, to be honest. For a 70 watt tube I need to run at 23 milliamps. And we've already tested this tube that we just had in there at over 23 milliamps. So I know that it will deliver the current that I require. And I'm pretty confident there'll have enough spark in it to fire the tube. Now, the other reason I chose this 70 watt tube is because this is 1250 long and the new tube is 1250 long, so I haven't got to make a new extension tube. Okay, now my machine has been switched off for well over an hour now, so I think it's reasonably safe to tackle these red wires. I'm always very nervous of them because I'm not an electronics or an electrical person, although I may have a magnetic personality. That doesn't make me immune from killing myself. This is 2.5 years of crap that's gathered on this silicon tube as it's been sitting in the back of the machine here. Yeah, I don't come around here and dust that very often. I think if I was going to get a shock, it would have jumped across and hit me by now, so I think I'm reasonably safe on there. Yeah, am I still talking? Yeah, I think so. So there was my original mechanical connection that I made. Now, I'm pretty fortunate in that the the tube connectors on here, these clamps, they're reasonably well made. So they do allow me to lift them up like that and withdraw my tube. The only problem is we've got two things to consider now. One, there's a water connection this end, and two, a water connection that end, and I can't get to it through there, so I'm going to have to take this end cover off. Now this is the water inlet normally, so water is being pumped up to this end. So if I tip my tube up like that and take this piece of tube off here, and hopefully most of the water is now running back down to the chiller. So if I put that down now, the worst that's going to happen is I might get a drip or two, which is right. So I should just temporarily take that there so that it doesn't leak. Means I can now, with a bit of luck, disconnect this end as well. Just plug that onto that little screw there for the moment. I don't need the tube, so I cut that off there, and then we'll sort this connection out in a minute. We'll put that away for a rainy day, I think. And here's the new tube, which we might as well slip in from this end while we're coming this way. Now I'll move that tube as far forward as I possibly can to that end, but I like to leave myself a finger width in there, like that, roughly put my palm in there. Now the other thing that we're trying to make sure we do is to put this water outlet to the top. Now they've arranged this very nicely so that everything is correct. They've got the water, they've got the connection at the bottom, which is already made off for you. You've got your wire at the top, which is brilliant. And we've also got our water outlet at midday, 12 o'clock, straight upwards, so that we don't get any bubbles trapped in here. Now, the ideal way to mount the tube is in something that they call quarters. And that means you take the tube length, divide it by 4, and you use 1/4 of that dimension to mount the tube here, and the other quarter of the dimension to mount the tube here. The basis of the argument is very simple. If you've got a quarter that way and a quarter this way, a quarter that way and a quarter this way, in the middle here you've got no stress because it's like a seesaw. But hey, we're not going to transport this halfway around the world, so we're not going to be too worried about that. We'll just use the existing mounts that are in here, which weren't specifically designed for this long tube, but it's not going to be an issue. I can plug the water back into this end, and we can also plug the water back into the other end. Okay, now down at this end, what I've done, I've taken this connection apart, and we've got half the fitting on one side of the wire and half the fitting on the other side of the wire that comes up from the machine. And now what I'm planning to do with these two wires, they're both very thin wires, as you can see. The insulation is very thick because we're resisting 25,000, 30,000 volts. But the amount of current passing through these wires is very small. We know it's only 25, 30 milliamps. So we don't need any heavy duty wire. And what I am going to do is to solder these two wires together, because there's no heat in the joint, so it's not likely to be a melting joint. Just to make life easy for myself, I'll just tape that down there. My third hand. Okay, so that's a nice solid joint now. We'll hide it about there somewhere. And that should be a completely spark-proof connection. I'll eventually tie wrap that back to the tube. So what I need to make this joint is a male bullet connector. So I'll just crimp that on there. And that's a fully insulated connection, so I'm going to do nothing more than leave that in the back of the machine here. Well, that's the tube back in. We've got all the connections made. Just check. We've got water out, we've got water in, we've got high voltage in, and we've got an earth cable. That's it. And we've got the tube mounted in. We're not sure that the tube is in the right position, height-wise, position-wise, but that's the next part of the exercise which people fear the most, aligning the beam. But if you follow some very simple and logical procedures, it's actually very straightforward. So okay, we're going to apply power to the machine again, and hopefully the first thing we're going to see is water filling up the tube for us. There we go. Lots of bubbles. I'm just checking along here and I can't see any bubbles. There are one or two very small micro bubbles sitting on the top, right on the top surface of the tube, which I don't think will cause any problems at all, because they're on the top side of the second tube in. They're sitting on the top of the water jacket. They're not affecting the heat transfer from the ionisation tube into the water jacket itself. Now, before I start messing around with the tube and testing it, I've taken my nozzle out so that the power is going straight down anyway. I've reduced the power to 15%, and I've got water in a little bucket here, so if the power does come all the way through here, which hopefully it should be, because I haven't messed up with the tube alignment too much, but it certainly won't be correct, then the power will be absorbed down there. Now, I've done some preparation work beforehand, and what I've got here, I've got some little cardboard targets which I've made, and these targets are a pretty snug fit into my mirror housing. So this is what I use to help align my mirrors with. Okay, now before we start the beam alignment process, what we're going to have to do is make sure we clean, or in my case, recondition the mirrors. These mirrors are molybdenum. They have a naturally reflective surface, crystal structure, which, okay, it gets maybe 1% or so lost if it's tarnished like this, but basically they are consistently somewhere in the region of 96-97% efficient at transmitting infrared light. There are 3 stages that you can go through to clean a mirror. Now, in every case you will need a cotton wool bud and some soft tissue. The cotton wool bud will carry out the cleaning action, and the soft tissue will remove the film that is always left by whatever cleaning agent you use. The most gentle cleaning agent that you can use is isopropyl alcohol, and you can use this on lenses as well. So if that fails to clean your mirror, there is another stage that you can go to which is slightly more aggressive, and here it is, acetone. You can do acetone cleaning on a mirror like this because it's molybdenum. You cannot use acetone on anything that looks as though it's gold coated, because the gold coating is very, very thin, so they may be more expensive to buy than these relatively cheap, and these are only about $5 each, mirrors. But hey, you can do all sorts of things with these mirrors that you can't do with the more expensive mirrors. What I'm just about to do to recondition this mirror might cause some people to turn in their graves. So just turn away and don't watch this next 2 minutes of video. Yeah, I'm going to be really aggressive with this mirror. I'm going to give it a little helping with some silver polish. Circular motion around the outside and towards the centre. You can hang on to the edge because the edge is never going to be seen by the beam. We'll just give it a quick final wipe with soft tissue. As I said, because this is molybdenum, you can be quite aggressive with it. And hey, here's looking at you, sunshine. Now remember what I said, the only mirrors you can attempt this with are molybdenum mirrors. So whichever method you choose to use, before you start your beam alignment, go around and clean all your mirrors. Now, it's probably going to take more time cleaning your mirrors and reconditioning them if you have to, than it will to actually align the beam. Beam alignment is actually a very simple process. There are 2 very simple stages and 1 more complex stage. So let's take the very simple stages to start with. Now, I can't show you mirror 1 from the back of the machine because it's just not the right angle to show you what's going on. But what we can do, we can peek through here and see what mirror number 1 is doing from the front of the machine. Okay, now I'm going to go around the back of the machine and I'm going to use one of my targets that I've already made, and we'll pop that into mirror number 1. As I said, it drops neatly into that mirror holder like that, and if I've got the dimensions right, it'll stick in there without a piece of tape. But if you need to, you can put a little teeny weeny piece of sellotape across the top just to stop it falling out. So I've got my power set to 15%, and we'll just give it a very quick pulse. There we go. Now, it's low. Am I worried? No. Is it central, left and right? Yes. Why am I not worried about it being a little bit low? We've got a mirror that is round, but the laser beam is not looking at the mirror like that. The laser beam is looking at the mirror like this, 45 degrees. So the height has not changed, but the width has. So I've got to be fairly accurate on the horizontal dimension to make sure that it stays in the centre of the available oval shape that the laser is looking at. We're looking at a circular shape, but that's not the same for the laser. So a couple of millimetres up or down from centre is not an issue. I'm going to leave that mirror as it is. I should be able to now very easily just pick this out of here, and if we're lucky, we take a look carefully at that mirror, we will have done no damage to the mirror at all. But if you can see any sort of spot or anything, little teeny weeny haze mark on that mirror, just go and clean it with a little bit of isopropyl alcohol. You need to be sure that it's clean before you move on. Now we're at the back of the machine, as you can see, because here's the laser tube. Right, now I'm going to move mirror number 2 as close to mirror number 1 as I possibly can. We'll put our target in there, and this time the target is just a little bit looser and it doesn't want to stick. And just catch it across the top of the target. Just stop it falling out. So we're going to do a burn, a little 15% pulse on target number 2. And again, we're so close to centre, within a millimetre or two of centre, that I'm not going to worry about adjusting mirror number 1. But I could, I'll tell you what, let's do it, because hey, we can. So what we've got on mirror number 1 is we've got 3 adjusters. Now this mirror is arranged very nicely, so we can adjust X and Y independently. Now if you've got triangular as opposed to L-shaped adjusting screws, you're going to have a little bit more difficulty. This is very easy because we need to first of all adjust the spot very slightly upwards. So to get it to go up, we've got to twist the mirror backwards. If we leave these bottom 2 screws alone, we can just undo the top mirror very, very slightly. Just make sure you undo all these adjusting screws, because we're not going to transport this halfway around the world, and these springs are going to lock it in place anyway. Now we just do another pulse to see if we've moved it up a little bit, and we have. Now we can move it very slightly to the left as well, and to move it to the left we've got to tip the mirror this way. So I've got to undo this one very slightly as well, and you saw how very slightly that was. And we take a look at our success by putting a new target in. Still a little bit low, so we can raise it up just a little bit more with a further tweak on that mirror there. The beam is approximately where we want it, in the centre. Now I wouldn't normally have gone to all that trouble because it was close enough to start with. Right, we've now completed what I call our sighting burn. What we're going to do is we're going to put a proper target mark onto mirror number 2 in its back position, as close to mirror 1 as we can. And there we go, it's pretty reasonably central. Now what we're going to do is move mirror 2 as far away as we possibly can. Leave that target in there with its target burn on it. And now I'm going to put another pulse on there. And what you've got to do is see how far that second pulse is away from the first pulse, we've got to adjust mirror 1 to make the 2 dots coincide. So we want that second dot to be on exactly on top of the first dot. So it's currently down here, and we've got to take it slightly left and slightly up. The way to imagine this is always a pair of hinges. So this is a door on hinges. So if we want the beam to go across this way, we've got to hinge the door this way with this one. So we've got to wind this one off very slightly to move the beam across. And then we want to move it up very slightly, so it's going to hinge across this axis here, and we want to move it backwards, so we've got to move that one out very slightly. So let's see what we've done. I think we may have succeeded, but there's only one way to find out. And that'll be to put a new target in there and repeat the process. Now it might take 2 or 3 attempts to get it spot on, but the closer you can get it, the better your calibration will be. So, close in, pulse. Step out. Let's see how good we are second time around. I think we're going to live with that. That looks pretty well spot on. So that's relatively easy to do, and what we've done, we've aligned the beam perfectly with that rail there, both in the horizontal direction and the vertical direction. Now we cannot, under any circumstances, touch mirror 1 again. End of story. This process that I'm showing you works forwards. You cannot come backwards and adjust anything. Now, when I remove my target from mirror number 2, you may see, I don't know whether there is any haze on there, is there? I will just give it a quick touch to make sure. We don't need to look at mirror number 2 because we've just set the beam to the centre of mirror number 2. And just because we twist the mirror very slightly doesn't mean to say we're going to upset the centre of the beam on mirror 2. What we're going to do is steer the beam off of mirror 2 onto mirror number 3, which is this mirror here. Okay, and we're going to adopt exactly the same procedure that we adopted before, except this time the targets that I've got are slightly different. I've got a small target here, and the small target hangs like a flag this time. And it hangs like a flag in there, like that. Okay, so it just fits neatly in there. And now we'll take the head as close as possible to mirror number 2. We're going to see how close we can get it to the centre of the target again. Pulse. Now it looks quite a long way out, doesn't it? Should I worry? Well, the answer is, in this case, no, I shouldn't worry. It's about the correct height, but it's out in X. It's probably out by more than 2 millimetres, it's probably 3 millimetres off centre. But let's not worry about that because I've got a secret weapon on this machine. So that was our target burn. Let's see how close we are with the next burn. Not far off. We're slightly high and slightly too far this way. So now we can go and adjust mirror 2. We want to come down, which means we've got to push the top down. And we want to go to the left, which means we want to drop that one back a shade. Let's see how successful my adjustments have been. Oh, too far to the left, so I've got to come back a little bit. A little bit more. Okay, now we've got to repeat the process again because we think we're pretty close. So if you get good at this, you should be able to do it in 2, but it might take you 3 or 4 attempts. Don't let it worry you. You'll just get better the more times you do it. So we need to make a burn close. This is our target burn that we're now making. Pulse. And now we're trying to do an alignment. We're setting mirror 2 with this second burn. So let's see how close we were now. See? I've done this so many times that I generally can do it in 2 hits. Okay, I hear you say, but you're a long way off centre. Yeah, okay. So what? Look, I've got 4 screws here. 1, 2, 3, 4 screws. There we go. I've loosened the screws off here now. Look, I can move the head forward. And now, close, but not quite. Just a shade more. About there. And there we go. Spot on centre. And I've just done that by moving the head. I'm catching the beam into the right place by moving and adjusting the head. Your head will have some Y adjustment on it, so you'll have no problem doing that. But what you won't have is any Z adjustment to make it true in that direction. And that's the other secret about this machine. I've got Z adjustment on here, which allows me to move up and down. Now at the moment I don't need this Z adjustment. I've just set X true to this rail here, both in that plane and in this plane. Otherwise the dots would not coincide. The dots coincided, but they weren't on centre, so I was able to move the head to catch the beam in the right place. If I didn't have that ability on this machine, I would have to go all the way back to the tube and move the tube around. It's just like snooker or billiards or pool. You know, you're going to bounce off of 2 cushions and get to here. If you mess around with one of them, you mess around with the whole lot. So you've got to go back and reset the whole of the beam again. Very, very tedious. And we haven't even started the most difficult bit yet. We've just done the 2 very simple processes, which, trust me, when you do it at speed and you've done it enough, without trying to explain it to people like I'm doing it to you at the moment, it's quite a fast process. I should be able to set this beam up from nothing to fully perfect in about 15 to 20 minutes. Okay, so we've got X and Y set perfectly. Now we've got to mess around with Z. Now most people don't consider Z as being difficult at all. It's just a few tweaks on here to get it through the centre of the nozzle, job done. I'm afraid it's not quite as simple as that, because you've got to treat Z exactly the same as you treated X and Y. And let me explain as we go through. Okay, so I've just removed my handle and the clamp screw off the end here, because with this design of head, I've got a nice, clear, clean stem to work with, which allows me to make a jig, which I've done out of some 2mm, I think it's 2mm thick acrylic, which allows me to put this jig on here like this. It's a snug fit, purposely. Push it up onto the second registration, like that. And now that's nicely registered vertically downwards, and that hole there is true to the centre of this axis. Right, now to start aligning the Z axis, first of all we're going to drop one of my larger targets under there. Now it doesn't matter whether it's true, centred or not. Provided the beam hits the target somewhere, that's all we're interested in. So we'll produce a pulse, and you can see it over the back there. We're now going, and that effectively is a target pulse. We're now going to drop the table down at least 6 inches if we can, somewhere like that. The further you take it down, the more accurate will be your setting, because very few people are going to be working with large Z-axis movements. So now we'll produce a second pulse. Wow. Not far out, but a little bit out. So we've got to come forward and across. And to do that, we need to push the beam, let me think. We've got to push the beam that way, which means we've got to twist it, allow it to come out very slightly. And we've got to take it that way, which means we want this to come out very slightly. Let's try again. Well, that's 2 attempts to get that right, and I've nearly got it on the second attempt, I think. So we'll run that one more time. Target burn. Still very slightly. There we go. Now I'm very confident that in 2 hits I've got that right. 3 hits I've got that right. Okay, so what we've now done, we've made sure that we've got the beam perfectly aligned, perpendicular to the z-axis, which happens to be the table. So wherever I drop that table up and down, the spot will always remain in the same position. But that's not the end of the story. We need to use one of these targets now in my special fixture here. And what we're going to do, we're going to put that in there like that. It just clips neatly in there. If we've got the beam coming in correctly here, hitting this mirror in the right place, it will go dead true down the centre of this axis here and hit the centre of my target. And that's what we're trying to do. We're trying to hit something that I call on that mirror the sweet spot. There is only one spot on that mirror where the beam will come and go perpendicular down through the central axis of the beam in both planes. It's not only got to be this plane, it's also got to be in this plane as well. We're a little bit out. The first thing you can see is we're very slightly out back to front. We can easily move the head in this plane here. So what we've got to do is move the head very slightly backwards to bring that beam onto centre. It doesn't matter that it's not true here, because that's not what we're worried about. We're trying to find the dead true position for it on the mirror. And we'll do just a quick tighten up on 2 of them, just so that we get the alignment right. We don't want to... A little bit more. A little bit more. That's pretty good this way. Now what we've got to do is move the beam backwards. And how do we do that? Well, the answer is quite simple. If we look at it from this point of view, the beam is coming down here. I'll exaggerate, it's way off centre, it's too far forward. If we want the beam to come further down the mirror, in other words, we want it to finish up here, look, what we've got to do, we've got to raise the head up to make the beam hit the mirror in here lower down. So I've got to raise this mirror up now, and as I raise it up, so I shall actually be moving the beam backwards. Okay, so we've lifted the head up, and let's see what effect we've had on the position of the dot. Well, I can't say any more than it looks as though it's spot on. So what we do, we'll take that one out, we put another one in. Just make sure it's sitting in there snugly, and there we go. So now we know that the beam is hitting the sweet spot in there, going right down the central axis of the tube, and is vertical or perpendicular to the table. That's perfection as far as Z is concerned. Almost. And we can now go back to reality and put a lens in there, because what the aim of the exercise is to make sure that the axis of the beam travels through the axis of the lens. I need to find out roughly where that clamps, which is about there, and I've got some marks on here anyway. Drop my lens tube down and put my handle so that it aligns with those marks. Okay, so I've now fitted my handle, and we've put a 2.5 inch lens in there. It doesn't matter what the lens is, but it's got a small hole in the end of the nozzle there, and what I've got here is a special final setting tool. I put a piece of tape on there, and I'll drop that over the end of the nozzle, and we'll do a pulse. And you can see that the beam is coming out pretty close to the centre of the nozzle, but not quite. Now that's a risk that we might be touching the beam on the edge of the nozzle and losing power. So what we've got to do is make sure that we just tweak this Z-axis very slightly, and it looks as though we might need to just move this one backwards. So we've got to twist it in to move the mirror backwards to get this to come across. So if we just put a small adjustment on there and do it again. Has it moved? No. Now it's come back onto centre more or less. So what we do, we can choose another one and we can check it again. Still could come across a little bit more. And there we go. This one here. So let's put some more tape on. So that's basically the final Z adjustment. If you're really looking for perfection with the setting of your machine, we should be able to do this. Back left corner. Pulse. Front corner. Pulse. 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 And finally, one right in the middle. Whoops. And there we go. That's pretty well set up. So I'm very happy with the beam alignment on that machine. Some parts of it are complex, but they're easy when you understand what you're doing. And I hope I've broken it down into sufficiently simple stages that you understand how the beam alignment needs to be set. If you don't have an adjustable head, excuse my language, you're screwed. Because you've got to go all the way back to the tube and you've got to adjust the Z height on the tube. And then you've got to go all through that procedure again. It could take you a day or more to fiddle around and find the right sweet spot on mirror 3, which is the key to this whole setting process. Now I've just dug up the specification for the tube that I fitted to this machine. Now I know that it's a Cloud Ray branded tube, but in reality I also know that it's manufactured by SPT, and here is the tube. In their range it's called a C70 tube, and I bought this as a 70 watt tube, and sure enough, just like many other Chinese manufacturers, I don't think they're really telling me the truth about this tube. It tells me it's a Model C70, which gives me the impression it should be a 70 watt tube. It's rated at 60 watts. So really, I've bought a 60 watt tube, have I? Mind you, it also goes up to 80 watts, but if there's anything like other manufacturers' specifications, people like Reci, EFR, what you'll find is that they give you these two numbers and they'll tell you that, hey, you can't use that power because that's a test power. You can only use this power or even less, otherwise you won't get the life out of the tube. So what am I going to find here? Well, a quick look down the specification tells me that it's a 1250 long tube, which is true, and that compares to the 1230 60 watt tube that I had in there before. 55 diameter, which is exact match as we found out, and this time they want to run it at 15 to 25 degrees C, which is a bit lower than some of the good quality tubes, and I use that word in inverted commas, good quality, where they allow you to go up to 40 degrees C. So yeah, I mean, I normally run up to a maximum of 30 degrees C, so I'm not going to change my rules just because it says 25 degrees C there. The operating voltage, we know that the power supply that I've got in this machine works adequately because, hey, the tube fires, we've seen that. Now this 1.1 is a reference to the quality of the beam. And when they say the quality of the beam, they mean the relationship of how close it becomes to a true Gaussian curve. As this number gets bigger, it's moving further and further away from this true Gaussian normal distribution shape. So at 1.1 we have got supposedly a very, very good match to a Gaussian distribution. Now it tells me that the starting current, the ignition current, is 4 to 5 milliamps. So we'll take a look at that when we have a look at our chart later on. And we've got a working current. Now this is the key thing, the working current, 15 to 20 milliamps. Now does that mean to say that at 15 milliamps I'm going to get 60 watts and at 20 milliamps I'm going to get 80 watts? We'll check that out shortly. What we've got here looks like a typical Chinese specification where they're not really telling you the truth. So I've just been in with my kit and I've done a calibration curve for this tube, and wow, so I think we need to take a little bit more of a detailed look at this curve in relation to the promised specification. The impression was that I would get 60 watts at 15 milliamps. At 15 milliamps I'm probably getting somewhere in the region of nearly 70 watts. So I'm already making this rated power specification at the minimum working current that they say, and it does say working current, it doesn't say test current, remember. So that means I could reliably go up to 20 milliamps. So if I go to 20 milliamps I'm already up here at about 85 watts. So that again is delivering more than the maximum power that they specify. I've yet to come across an SPT tube or a Cloud Ray tube, whichever way you want to look at it, which delivers less than the specification. They always deliver more, and I've seen quite a few of these calibration curves from various people that have bought these tubes. So I was fairly confident I was going to get a good performing tube, and hey, you can see that I've got one. Now the only thing that we haven't tested at the moment is what the mode burn looks like. Okay, now we'll do a 15% burn on here to compare with the 15% burn that we had previously. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, although I could use 90% power, I've set the max power to 85%, which is a number that I used to use on this machine with the previous tube. So we'll just take a quick look and see what that comparison looks like. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, there's the 10-second performance for the 3 tubes. That's my 70 watt Mactron tube in the China Blue machine, That was the 60 watt EFR tube in the Lightblade, and now this is the 70 watt SPT tube in the Lightblade for comparison. There is none. As far as dots are concerned, well look, I've got my point back. It doesn't seem quite as powerful as this one, but maybe that's a good thing for engraving, because maybe I've got more control. The final test will be to do my Foxy picture on this machine to see just how good it can come out. So was it worth it? I think the answer is very definitely yes. This is the final result of just my first attempt, a quick guess at what I thought the values might be. I suspect I should be able to refine this quite a lot more and make it slightly darker without getting overburn on the dots. I've done a few experiments down here, as you can see, with my little dot pattern, and it was quite amazing the difference between this and this one, which was done on the China blue, and this was the tube that I took out before. Now if we take a look down here, for example, you can see we've got detail in these hairs, which we can also see on the China blue machine, but we couldn't see it here previously. The strange thing about this was that I had to change the settings on the lens. Previously with these, I've always set these to around about 11.2 millimeters beyond the nozzle. With this one, I had to set it about 11.8 or 11.9 millimeters beyond the nozzle. So that was indicating to me that we've got a much sharper energy profile right in the center. At 11.2, I was getting quite thick lines, but it wasn't until I increased the focal distance to 11.9 that the line got as thin as I could possibly find it. The focal point doesn't change, but the energy density at a given point away from the nozzle changes, and so consequently that's why I had to readjust my focus. I'm very pleased with this at a first attempt, and I'm very confident that within another 2 or 3 attempts at doing this, I'd be able to get it even crisper and darker. This compound lens is not designed for cutting. It's got a very narrow focal range. I'm giving this full beans, 80% power is about 84 watts at 40 millimeters a second. Wow, look how clean that cut is. Now I've got a lot to learn about this tube, its characteristics. It takes a little while to find out about a tube when you've been using something else for quite a long period of time, and it naturally becomes ingrained in your brain, the power, the speed for each material. Well, thanks very much for your attention and your time, and I'll see you in the next session.